All right, guys. So the Super Bowl is set. Chiefs, Eagles. We know that the trend for the Commanders to not follow through, the one where the domination in the divisional round contributes to this Super Bowl run. That trend did not continue, and so our Super Bowl is now finalized. Chiefs, Eagles, where the Eagles have defeated the Commanders in the championship round. So we have Chiefs, Eagles, and now we're going to go through a couple of these different trends that support my prediction of the Eagles winning the Super Bowl. Now, like we predicted the Commanders to win, this Super Bowl and Super Bowl trends in general are much more favorable and are much more likely to occur because it's the culmination of the entire season. It's the final game. It represents what all of these teams have been waiting for. One team emerges victorious, and it's the final grand stage of the NFL season. And so, a lot of these trends that we're going to be discussing here are really applicable to the Super Bowl, and they apply very well to the Super Bowl. Some games, or even some playoff games, some regular season games, you may see some trends not following through, but the Super Bowl is really where you see the trends happening because they're the best teams. It's the final game of every NFL season, so we see these trends continuing onwards, and they're able to exist for a long period of time. So when we go with the Chiefs and Eagles. Why am I going with the Eagles here? Number one is that there's never been a team that has won three consecutive Super Bowls, right? Three consecutive Super Bowls has never happened, right? I don't think that's going to happen with the Chiefs. Another thing is that the last undefeated team in the regular season has never won the Super Bowl. The last undefeated team in the regular season has never won the Super Bowl. And we've seen this with the 2018 Rams. We've seen this with the 2018 Rams, where they were the last undefeated team in the regular season. They lost to the Patriots in the Super Bowl. We've seen this with the 2019 49ers, last undefeated team in the regular season, lost to the Chiefs in the Super Bowl. We've seen this with the 2022 Eagles, last undefeated team in the regular season, lost to the Chiefs in the Super Bowl. We've seen this with the 2023 Niners, last undefeated team in the regular season, lost to the Chiefs in the Super Bowl. This year, Chiefs, last undefeated team in the regular season. My guess and my prediction is that they will lose to the Eagles in the Super Bowl. The Eagles will emerge victorious. So these are the two major trends that we see in the season throughout Super Bowl history where a last undefeated team in the regular season has never won the Super Bowl, and B, three consecutive Super Bowl winners has never occurred. So that is the rationale behind the trends of my prediction here. So that's why I'm going with the Eagles. And let's now talk about Exam FM. So if we look at FM, there's concept of annuities, which are payments for end periods of time or perpetual in the case of perpetuity, it's for an infinite amount of time. When we talk about annuities, we know that there is an annuity immediate, which represents uh, a payment one period after it is valued. So the present value could be at time zero, the first payment will be at time step one, and so on. We know that that is different from an annuity due, which represents the first period and is valued at the first period of the payment. So if the first period of the payment is one, the present value is going to be at one. You're going to calculate the present value at time period one. And so we know that annuities are extremely common in exam FM. One of the main formulas you need to know about annuities is not just how to calculate annuities through your TVM or what the general formula is, but you also need to understand what the formula for a perpetuity is. A perpetuity is an annuity that continues on forever. There's no fixed n number of periods. You can think of this as your payments are ongoing continuous for an infinity periods. And so how do we get the present value of that? Well, if it is an arithmetic progression up to infinity, then we can get it by taking the present value, or not the present value, by the first payment, dividing by the interest rate plus q over I squared, where q represents the difference. And so we're able to use this to get to our present value of an arithmetic progression to infinity. In the same way, we have a geometric progression to infinity, where if we want to calculate the present value of this geometrically increasing or decreasing sequence, and it's going on for infinity, there's no fixed n. We're able to get that by doing 1 minus 1 plus k over 1 plus I, and you notice here that I is greater than k, or it should be greater than k. Now, if as we let n approach to infinity, in the case where I is greater than k, this will always be less than 1. And if this is less than 1, right? If this is less than 1, and we keep on taking powers of that to the first power, second power, third, and as we let that approach infinity, this entire term will approach 0, and we're left with 1 over I minus k, and we multiply that by the first payment that we made during that time step. So as an example, if we've made payment here at time step 1 of p, and then we're going to increment by a factor of k, we're going to have an interest rate of I. Throughout these infinity time steps, we're able to get the present value. Present value at time 0, not at time 1 where the first payment is made, but one period before the first period is made. And so that's where we're able to get the present value from. And so we talked about how to get the present value of a perpetuating arithmetic increasing an arithmetic sequence perpetuity. We talked about how to get to the present value of a geometric progression or a geometric annuity or a geometric perpetuity. So those are the two concepts, arithmetic, geometric, how to find the present value that we know. Another main idea is of bonds and loans. So in this, typically one of the main ways you want to tackle these problems is by creating a diagram of how you're going to go through defining the terms. So we have the duration, so which measures what time step you're at, which is 0 to n. We have the payment, so this represents the payment that you're going to make at each time step. So for in the case of bonds, it will be your coupon payment, or in the case of loans, it will be your regular payment R. Another thing to know about these payments is that sometimes these payments can change, in which case the principal repaid will be the same, or they may be different, right? So if these payments are different, it's possible that the principal repaid is the same. If these payments are the same, the principal repaid will be different. So depending on which one of these two are different, you're able to allocate the equation to the other term. So we have duration, we have payment. Typically, payment is constant throughout. FR and R for bonds and loans. Then we have our interest due, and our interest due is always going to equal the interest rate times the previous outstanding balance. And another way, in the case of loans, it's going to be R times 1 minus Vn minus T plus 1. In the case of your bonds, it's going to be F. In the case of bonds, actually, the only formula you need to know is this one. And then if we are referring to principal repaid, which in the case of bonds, you can think of that as your write up or write down. So principal repaid is going to be RVN minus T plus 1. And then your write up or your write down is going to be your FR minus CI VN minus T plus 1. You can think of a write up. You can think of a write up as going from P to C. And if you're going from P to C, that means C is greater than P is less than C. This is a discount bond. If it's a write down bond, then you're going from P to a lower level of C. So your P is greater than C. This is a premium bond, right? So you can identify if it's a premium bond or a discount bond simply by detecting if it's a write up or a write down, which you can get from what is the initial amount at duration 0 and where's the ending amount that you're trying to get to. And now that's our principal repaid. If we go to our outstanding balance, we have R times AN for loans, and this is what we call the prospective method, where we are discounting the future cash flows. We're saying these are the number of payments that need to be made. At a high level, outstanding balance is the present value of the future cash flows. So by definition, this is the annuity, this is the payment. Now, another way to do this is we can first accumulate the loan by some amount of interest, and then we can subtract the accumulated payment. So we take the accumulated loan amount, right? And from it, we subtract the accumulated payment to get the remaining period payment that is left to be made, the present value of the future cash flows. Another way to do this is if we take, let's say, outstanding balance at time step t, we take the previous outstanding balance, we subtract it, the principal that we have repaid, and that will give us the outstanding balance at time step t. One of the things to note is that the sum of all principal repaid at all the timestamps is going to be equal to the original loan. Going to be equal to the original loan, because if we think about the principal repaid, what is it paying? It's paying everything of the original loan. And then the interest due is the amount that is accumulated based off of the time factor, right? So if we take into account if we add up all of the interests that we have to pay, if we add up all of the principal repaid that we have to pay, which is the original loan itself, we can get to the total amount that we have to pay, which is the sum of the payments in the payment column that we talked about before. Next, if we talk about the same principle in bonds, we have a similar principle as well. We're able to get the outstanding book value by taking the previous book value, subtracting it by the write-up or write-down amount. Another thing to note is if we want to get the outstanding balance or outstanding book value, another way to do that is we take the previous book value or outstanding balance, we increment it by interest, so we multiply by one plus I, then we subtract the coupon payment or the original payment of R. And so this will also get us to the same answer. And then another way to use your TBM keys is you know what the future value is, you know what the present value is, and the present value will be the outstanding balance at, let's say, time 8. Future value will be the outstanding balance at time step, let's say, 16. This will be positive. Payment will be positive. This will be negative. You can think of this as the amount that you're giving up front. Payment is what you're receiving. Future value is what you're receiving. And you can think of this in the same case of bonds, right? Where you have this present value, the price of the bond, and then it's going to give these coupon values, and then at the end, it's going to give this final redemption amount. So that's one of the things we learned. One of the main paradigms of tackling these types of problems is visualizing that diagram in your mind, trying to think about what are these different terms, how do each of these terms relate to each other? Can I find a pattern in these different terms? For example, if I'm able to identify that, hey, this is a geometric sequence or this is an arithmetic progression, am I able to take advantage of that? What do certain terms sum up to? Can I take advantage of that? Is this payment constant or is this payment constant? And what does this mean about the other payments? Using those characteristics to make easier equations and easier assumptions that you can plug in very efficiently, that's going to give you the answer quickly. So that's one of the things we want to keep in mind, is that even in these tough questions, when the problem statement gives you something that's already given, right? It gives you something. Can you use that and try to see what other idea or what other assumption can you already make or can you already fill in? For example, if the problem statement says that, hey, the sum of all of the principal repaid from this amount to this amount is, right, X. Another way you can think about that question, right, is if we go from this outstanding balance, right, And then we subtract off all of this outstanding balance. We should be left with the outstanding balance at this step. And so because of these paradigms of thought, you're able to convert these questions into new assumptions that you can make to help solve the problem in an easier manner. And we've already mentioned bonds, talked about bonds. We know about topic 5 about spot and forward rates. We also know about Macaulay duration, MACD. We know that MACD it's the represents that in general relative what is the time frame or the time period with which you're going to get your payments. So it doesn't take into account the value of the cash flows, but rather the relative nature of them in regards to when those cash flows will be paid. So if we have a single cash flow at time step 5, Macaulay duration for that will be 5 because we have a single cash flow there. So that's MACD. We can get mod D by doing MACD times V. We're able to get mod C by doing V squared and max C. That's MACD. This is an important relation to understand. Able to get mod C by taking the second derivative of price equation. And we're able to get mod D by taking the negative first derivative and then dividing it by the regular price equation. And then that's at a high level. If we quickly go over some statistical significance testing, the reason why we have statistical significance testing in the first place is because whenever we have two different groups of populations, whether we have two different samples that we're trying to measure, two different groups of data points, and we want to know, is there a difference, a statistically significant difference between these two groups of data points, such that that difference could not have occurred by chance? Did this occur by chance? Or is there some systematic nature to this? Is something else going on? Is there a systematic pattern or structure that's different within these two groups that allows us to have this difference? And so that's why we have statistical significance testing in the first place. It provides a more statistically sound way to measure those differences between different groups, because you could just compare the percentages or you could just compare the proportions, but how do you know if that is not likely due to chance in a more sound and strategic and statistically sound method? That's why we have statistical testing in the first place. We also have PCA to reduce the dimensionality of your data set. Now, PCA is important because whenever we're working with many of these large data sets, we're not going to have like a few columns or a few features. We might have 1,000 features. You might have 1,000,000 features when you're working with large complex data sets. And all those features might not be important in identifying what the crux of the data actually is. And so how can we get to the crux of the data without considering all of the features? That is through dimensionality reduction. How can we take a large group of data points, a large group of feature space, a large feature space that we have, and condense it into small, maybe one or two principal components, or more, but fewer features that's able to capture a lot of the variation of our data points. So it's not taking away much of the information; it's actually capturing a large portion of the information in fewer features, which helps in model development, also helps with visualization. If you have a 10 million row data set that you're trying to actually visualize, you're not going to be visualizing, right, 10 million features. If you can condense that into a 3D PCA plot or a 2D PCA plot, you'll be able to better visualize that data set. So it's also a very good technique for data visualization. Also a very good technique for clustering. We know many of these different clustering algorithms, k-means, dbScan, they're all very good at their own respective ways. We know that how k-means works is it first and it randomly initializes all of the different centroids. It then says, okay, we have, let's say, a k of 3, we want to identify 3 centroids, randomly places those centroids, and then assigns the data points to the closest centroid, recalculates the centroids, then assigns all the data points to the closest centroid. It does that iteratively until you get to the point where, and 2 iterations, the group assignments of the data points to the clusters do not change. So once you get to a point where the group assignments don't change, your algorithm has converged and you have completed k-means. One of the things about k-means is because you have this random initialization of these data points, when you run k-means more than once, you could have two different clustering results. And so this is one of the drawbacks of k-means is when you have a large data set and you run k-means more than once, you may get different results. So one of the things is if you just have a random seed, you're able to reproduce the random initialization and you're able to get the same results each time you run it. dbScan is different in that A, it doesn't require the same level of uh, clusters that you provide to k-means. What it does is it starts with an epsilon value and a radius value, and it sees how many points are within a set radius and how many of those points are also within a set radius and a minimum sample of points. And then it continuously branches out and gathers those points to form a cluster. So if we have a point here, what it's going to do is it's going to say how many of these other points are within this certain radius. And if we get to, let's say, a certain number that's greater than some min samples parameter that we provided, then those become a part of the cluster. Then we see, okay, of those points, how many neighbors are within this set radius? And of those points, how many of those neighbors are within this set radius that are also of this min samples parameter, that the quantity is min samples. And then we cluster all those together, and that's how we get dbScan algorithm. And one of the main advantages of dbScan algorithm is it's able to cluster more dense populated regions that are actually non-spherical that have irregular shapes. And so that's what dbScan is able to do, is able to identify high dense regions. So if we have this region, if we have this region, yeah, Euclidean distance wise, this point is actually a lot closer to this point. But in terms of density, this region is of the same density, and this region is of the same density. So dbScan groups data points in terms of density, in terms of local density, local collection of points through understanding radius, through understanding what points are within a certain radius of a given point, while k-means focuses on centroids, which collection of points are closest from a Euclidean distance to that centroid, and it assigns those data points to that cluster. So that's dbScan. K-means, talked about that, talked about some PCA importance of just statistical testing, talked about some exam FM materials, and then we also went over trends for why the Eagles will win the Super Bowl. So that's really all I wanted to cover. I'll see you in the next video.